Okay, let's dive into a statistical mystery that can drive you crazy. Picture this. You've built a model, you're running your checks, and then two of your most trusted tests give you completely opposite answers. One is flashing a big red warning light, and the other is giving you the all clear. So what do? How can two established tests look at the same exact data and come to such different conclusions? Well, we're going to get to the bottom of it. And this isn't just some textbook problem, by the way. This is a real question from a real person on the stats forum, cross-validated. And it's a classic. It trips up so many people. You've got the Bruce-Pagan test basically screaming, hey, you've got a problem here, while the White's test is just shrugging, saying, nope, everything looks fine. It's a perfect statistical contradiction. And this really gets at a much bigger issue, right? What are we supposed to do when the very tools we depend on for clarity seem to be arguing with each other? To solve this puzzle, we really have to understand what each test is looking for and, more importantly, why they might see the world in completely different ways. So before we can figure out what went wrong, we've got to understand what right is supposed to look like. In the world of linear regression, there's this set of golden rules for how our model's errors should behave. When our data plays by these rules, our results are basically as good as they can possibly get. It's the big promise of our standard models. And the hero of this perfect world is a concept called homoscedasticity. Yeah, it's a mouthful, I know, but it stands for a really simple and beautiful idea, that the spread of our model's errors, the variance, is constant. It's predictable. It means that no matter where you look across your data, the amount of random noise is pretty much the same. Now, this idea of homoscedasticity is just one of several key ground rules, which are all part of what we call the Gauss-Markov assumptions. For this ideal world, the rules are pretty simple. On average, our errors should be zero, they need to have that constant variance we just talked about, and they shouldn't be related to each other. When all these things are true, something really special happens. See, when all those conditions are met, the workhorse method we all use for fitting our model, ordinary least squares, or OLS, it earns this really cool title. It becomes blue. And trust me, blue is the gold standard. It's exactly what we're aiming for. So what is blue? It stands for Best Linear Unbiased Estimator. Unbiased just means that on average, our estimates hit the true value. They're correct. And best means they're the most precise estimates you can possibly get. They have the smallest variance. It's the best of both worlds. But you knew there was a but, right? The real world is messy. Our data rarely follows all the rules perfectly. And one of the most common ways things go off the rails is when that key assumption of constant variance breaks down. And this is where we meet the villain of our story, heteroscedasticity. And this visual just shows it perfectly. Look at the left. That's our ideal world, homoscedasticity. The errors just look like a random cloud of static, totally even. But now look at the right. You can see that classic telltale sign of trouble, the funnel shape. As the value on the bottom axis gets bigger, the spread of the errors gets wider and wider. The variance is definitely not constant anymore. So what's the big deal? Well, the consequences are actually pretty serious. Your estimates are still unbiased, which is good. Think of a darts player who, on average, hits the bullseye, but their shots are scattered all over the board. That's what unbiased but inefficient means. But here's the real kicker. Our standard errors, the way we measure uncertainty, they become totally unreliable. And that means all our p-values and confidence intervals are basically invalid. You just can't trust your own conclusions about what's statistically significant and what's just random noise. Okay, so to avoid that disaster, we obviously need to test for this problem. And this brings us right back to our two detectives from the original question, the Bruce-Pagan test and the White test. They're both designed to hunt for this exact problem, but as we're about to see, they go about it in very, very different ways. Let's think of the Bruce-Pagan test as our specialist detective. It shows up to the crime scene with a very specific theory. It's looking for one particular kind of evidence, a clear, linear pattern where the error variance grows or shrinks in a straight line with our variables. It's incredibly powerful when its theory is right, but it can easily miss other kinds of clues. The White test, on the other hand, is the generalist detective. It shows up with no preconceived notions. It just starts searching the entire crime scene. It's not just testing the original variables, it's also looking at their squared values and all their possible combinations and interactions. It's way more flexible and can spot almost any pattern of trouble. And there we have it. We now have all the clues in front of us. We know what the ideal world looks like, we know the nature of the problem, and we know the different methods of our two detectives. We can finally solve the mystery of why they gave such conflicting reports. This table right here is the absolute key to the whole thing. The Bruch-Pagan test is a specialist. It's laser-focused on finding linear patterns. And because it's so focused, it has a ton of statistical power for that one job. But the White test, it's a generalist. By testing everything, the variables, their squares, all the combinations, it has to spread its statistical power really, really thin. It's like trying to listen for one specific whisper in a giant noisy room. By trying to hear everything at once, you might just miss the one voice that matters. So, here's what happened. In our user's case, the problem was most likely a simple linear form of heteroscedasticity. The specialist detective Bruch-Pagan was perfectly designed to find that specific clue, and it confidently raised the alarm. But the generalist detective White was so busy checking every nook and cranny of the model that it just missed it. Its power was too diluted to find the evidence and declare it statistically significant. Okay, so mystery solved. Bruch-Pagan was right. We found the problem. Now, what on earth do we do about it? Well, let's talk about the modern and by far the most common solution. We use something called heteroscedasticity consistent standard errors, or what pretty much everyone just calls robust standard errors. And the idea is really clever. Instead of trying to change our model, we just adjust the way we calculate our standard errors. It's a way of correcting our statistical yardstick to account for the messy data. This makes our p-values and our confidence intervals trustworthy again. And here's why this is so important. Just look at the difference in these numbers. The original classical standard error was less than 1, but every single one of the robust versions, which correctly account for the problem, are all about 33% larger. And a bigger standard error means a smaller test statistic, which means a bigger p-value. A result that looked significant before might not be significant at all once you use the right math. This is a huge deal. So you might be thinking, okay, why don't we just use these robust errors all the time, just in case? Well, they're not quite a silver bullet. For one, they can be a bit unreliable in really small samples. And if your data really is perfect, they're actually less precise than the old school ones. But the most important reason is this. Using robust errors can sometimes be like putting a bandage on a much deeper wound. And that leaves us with a really big takeaway here. Robust errors are an amazing tool. They fix the math so we can trust our tests. But the presence of heteroscedasticity itself might be a symptom, a warning sign that something more fundamental is wrong with your model. Maybe you're missing a key variable, or maybe you've assumed a straight line relationship when it's really a curve. So the crucial lesson is this: before you just patch the problem, always ask why it's happening in the first place.